And actually I'm going to prove it, so it can be a theorem. The fact is that the gradient vector is orthogonal to the level curve and let's underline the two words orthogonal to the level curve f of xy equals k, okay, at some point, and the point will be x sub 0, y sub 0. Okay, so this will be fact number 1. Fact number 2, the gradient vector is orthogonal to the level surface f of x, y, z equals k at some point x sub 0, y sub 0, z sub 0. All right, the key, the words that I underline is orthogonal and level curve when you have a function of 2 variables, or level surface when you have a function of 3 variables. And let's try to understand the difference between the two. Well, if you look at the hill that we just talked about, or the hill that I gave you at the beginning, the example, the first example with the topographic map. Well, essentially the height is a function of x and y. So z equal f of x, y. And when we have a level or a contour, that will be a curve. So it will be a level curve. On the other hand, if you have a function of 3 variables, okay, think about an expanding balloon. Okay, the surface of the balloon is a function of 3 variables. So as you expand it, what happens is that surface changes. And you can say that, okay, what will be the surface level? Well, that will be the surface at, let's say, time t equals 1 second, as we continue to pump air into the balloon. After, let's say, 2 or 3 seconds, we have a different surface. So we call it surface level. Well, that's one way to explain it. Another way to explain it is, say, some of you already took physics, and you have a magnetic field, or right? And of course, you have a field, but we're talking about field, but this is really in a 3-dimensional space. And well, let's say that you have electrostatic field, and the potential change depends on your location. For instance, you have some sort of induction, and as you pick up a different point, x, y, z, you have different level of potential. Same with gravity, if you think about it. Gravity is also a vector field. So what happens when you have something like this? The level, the function will be f of x, y, and z. And for a specific value of this function, you have f of x, y, z equals some constant k. That will be the surface level. The same as saying f of x, y equal a constant k. That will be a curve level. All right? Make sense? A little distinction. So what does it mean, this particular fact or theory? It means that the gradient vector is always perpendicular to either the curve or the surface, okay, for fixed value of the function. So if a function is z equal f of x, y, for a specific value of z, you have a curve, right? For instance, the circle will be x squared plus y squared equals 1, 2, 3, whatever. that will be a curve. The gradient vector will be perpendicular to the surface. In other words, it will be in the direction of the radius. When you have a surface, okay, then the gradient vector will be in the same direction as the normal. It will be orthogonal or perpendicular. How we prove that? That's actually fairly easy to prove. This notion, we're going to say the following. We take the function in a parametric form, and we're going to say that suppose you have a function f of t equals a vector such as x of t, y of t, z of t, right? Like so. So, and what you see here is this is this is a vector equation for a particular surface, okay, and the surface level will be this equals to some constant. All right, so we're going to take the derivative. Actually, I want to present it like so: is f of x, y, and z as a function rather than a vector. That will make it a little bit easier. So let's change these to a function like so. And let's take the gradient. The gradient, well, let's apply the chain rule first. And this equals to k. This is the surface level, okay? F of x, y, z equals k. So I'm back to right here, except x, y, and z are all function of t, and then apply the chain rule, which I got it smeared here. So let me rewrite. Apply the chain rule, and what you have is you have del f, del x, del t, then plus del f, del y, del t, plus del f, del z, del t, and the derivative of k equals 0. All right. Now, what we do have here is really a dot product. If you look carefully, you can break it down into del f, del x, del f, del y, del f, del z, dot, del x, del t, del y, del t, del z, del t. And it's equal 0. So you have two vectors. If the dot product is 0, then the vectors are perpendicular to each other, right? So right off the bat, you know that this is these two vectors are perpendicular or orthogonal. On the left side, what do we have is the gradient of f, right? Like so. What is the other one? What is this one? What is del x, del t, del y, del t, del z, del t? What kind of vector is that? I'm sorry? It's the derivative of r, of a vector r, right? And it's equal to 0. So the conclusion is the gradient vector is perpendicular to k. But what's the implication? R prime, the vector R prime, is parallel to the tangent to the surface. Right? So it tells that the gradient is perpendicular to the surface. And if it's two variable, then the gradient is perpendicular to the curve. Okay? So, and that completes the proof. Okay? Or the conclusion is gradient vector perpendicular to either in three variables, it will be tangent to the surface. Or curve. Depends on the number of variables. Yeah. To visualize this, if in 2 dimension, if you have a curve like so, right? And you pick up any point, let's say P, random on the curve, the gradient vector will be in this direction. So this will be the tangent, right? And the gradient will be in this direction. So this will be the direction of R prime, and this will be the direction of del F of xy in this case. Right? It's tougher to draw it in 3 dimensions.